Hello everybody, my name is Iman at SID. Welcome back to my YouTube channel. Today we're going to go ahead and start chapter 20. Chapter 20 is all about carboxylic acids and its derivatives. Now, carboxylics are compounds that possess this COOH group that you see in the center here. The COOH group, where you have a carbonyl and an alcohol group attached to that. Now, in this chapter, we're going to cover the reactions of carboxylic acids and their derivatives. We are going to cover preparation of carboxylic acid and its derivatives. And we're going to talk about the properties of carboxylic acids and, of course, you guessed it, its derivatives. Now, we're going to start off first with the properties of carboxylic acids. We're going to cover structure, acidity, and substituent effects. Now, as for the structure, the carbon atom of the carboxylic acid group is sp2 hybridized. And you can guess it because it has a double bond to it. All right, and therefore it exhibits trigonal planar geometry and it has bond angles of nearly 120 degrees. All right, now as for the acidity, carboxylic acids exhibit mildly acidic protons, and the pKa of these carboxylic acids is anywhere between 4 and 5, somewhere in that range. Now, as for substituent effects, the presence of electron withdrawing substituents can have impacts on the acidity of carboxylic acids. And this has a lot to do with inductive effects, and we're going to see a couple of these examples here. Now, onward to preparation of carboxylic acids. We've covered actually a lot of techniques in previous chapters on how to prepare carboxylic acids. We're going to review 3 of these techniques, and we're actually going to introduce 2 more preparation methods. Now, as for review, you can prepare carboxylic acids via oxidative cleavage of alkenes. So, oxidative cleavage is going to break that triple bond, and it's going to form as a consequence to carboxylic acids. And the reagents you need for this is O3 and water. Now, another way to prepare carboxylic acid is oxidation of primary alcohol. So if you have a primary alcohol like right here, you can treat it with, say, sodium chromate, sulfuric acid, and water, or another, like there's a variety of strong oxidizing agents, this one being a very important one that is commonly used. And what you can do is now oxidize that primary alcohol, and it will produce a carboxylic acid. Now, the third preparation method that will serve as review for this is oxidation of alkyl benzenes. If you have this alkyl benzene, all right, where the benzylic position at least has 1 hydrogen, what you can do is completely oxidize it to give you benzoic acid. All right, so any alkyl group on an aromatic ring will be completely oxidized to give benzoic acid, provided that there is a 1 hydrogen at least at that benzylic position. Now, we're going to add 2 more preparation methods in this chapter that you're going to learn that are new. And one will be hydrolysis of nitriles. Hydrolysis of nitriles will produce carboxylic acid. So, when treated with aqueous acid and heat, all right, a nitrile, that means a compound with this cyano group, can be converted into a carboxylic acid. So this is another preparation method of carboxylic acids. Something else you can do is carboxylation of Grignard reagents. This will also produce carboxylic acid. So carboxylic acids can be treated when prepared with a Grignard reagent and carbon dioxide, and this in combination will give us a carboxylic acid. All right, and this one's very important. This is going to reappear in a lot of the synthesis problems we may do in chapter 20. All right, with that being said, actually, let's go ahead and do a couple of practice problems to make sure, we have truly refreshed our preparation methods of carboxylic acids. Here we say identify the reagents you would use to perform the following transformations. We're starting off with good old ethanol. Ethanol looks like this. And we're trying to convert it into acetic acid. All right, and this is what acetic acid looks like. All right, what can we do to convert ethanol to acetic acid? Well, ethanol here is a primary alcohol. All right, and we're trying to convert our primary alcohol into a carboxylic acid. We know how to do this, guys. What we need is a strong oxidizing agent, something like sodium chromate, sulfuric acid, and water. This will convert our primary alcohol into a carboxylic acid. This will perform the reaction we need here. Fantastic. Let's do this next one. This says toluene. All right, we know what toluene looks like. All right, well, we're going to draw that out. Here's toluene. We want to get it to benzoic acid. All right, fantastic. There we go. All right, now we know how to do this as well. All right, we have this toluene group, okay? And we want to convert it into carboxylic acid. Now, our benzylic position, guess what? It has a hydrogen. So we know how to do this. We just learned that if we have a benzoic position that has a hydrogen, what we can do is oxidation of alkyl benzide. All right, now what we need for this is sodium chromate, sulfuric acid, and water. It's going to take our alkyl group on our aromatic ring and completely oxidize it to give us this carboxylic acid that we want. All right, so once again, all right, we're going to use sodium chromate, sulfuric acid, and water to perform this reaction. Fantastic. All right, let's do a few more. All right, identify the reagents you would use to achieve each of the following root transformations. Fantastic. Okay, starting off with the first one. Alrighty, we have this, and we are ultimately trying to get this starting material to look like this. All right, fantastic. Now, here's the process that we're going to use to do this. All right, what we have here, all right, is Br attached to this aromatic ring. All right, now we know something really cool here. All right, we know how to do carboxylic acid preparation with Grignard reagents. And Grignard reagents usually take on the form of MgBr with some sort of R group. All right, we have this R group, we have Br. We can get it to be a Grignard reagent if we simply introduce magnesium. And if we do that, what we get is MgBr attached to this R group. Fantastic. Now, we know how to take this and convert it to a carboxylic acid. We just covered this in our carboxylic acid preparation. CO2 and hydronium will perform this for us. All right, it'll take our Grignard reagent and convert it to a carboxylic acid. Beautiful. Now this is easy. If we're trying to take a carboxylic acid, convert it back to a primary alcohol, all right, we know how to do this opposite reaction, okay? We know how to take a primary alcohol, convert it to a carboxylic acid, sodium chromate, sulfuric acid, and water. But we want to go in the opposite direction. Now we have our carboxylic acid. We want it to be a primary alcohol. We have to reduce it now, all right? And we've covered a very powerful reducing acid in previous chapters. All right, we're going to use this again. Lithium, aluminum hydride, and water will get this done for us. Fantastic. Let's do one more for good measure. All right, so I'm going to erase this so we have room. And we're going to go ahead and do B. All right, let's erase all of this. And we're going to try to figure out how we are going to accomplish transformation B. All right, we're starting off, all right, with toluene. All right, we're trying to convert it to this primary alcohol attached to our benzene ring. Okay, so now what we want to do is we can do a few things here, all right? And this goes back to the idea that you can actually do synthesis problems, right? Like these right here, multiple ways. And you just have to figure out what you like and what you prefer, all right? Now, here's one way we're gonna do it, and I'm gonna leave it up to you to try to figure out another way to do this synthesis, all right? I'm gonna do it one way. We're starting out with this toluene, right? We know how to convert, all right, this aromatic ring that has a benzylic position with hydrogens to carboxylic acid. We know how to do this, all right? What we need is a strong oxidizing agent like sodium chromate, sulfuric acid, and water to convert this toluene into a carboxylic acid. All right, we know how to do that. And now we know exactly how to convert this carboxylic acid into a primary alcohol. All we have to do again is reduce it. And we can do this, with lithium aluminum hydride and water. Now, there are other ways to do this synthesis problem. I want to know how you would do this synthesis problem that is different than this reaction. All right, leave your answer in the comment section below and we can have a conversation about it. All right, but this is one way to do this problem. All right, now we want to move on. All right, now we want to segue into nomenclature of carboxylic acids and its derivatives. All right, so we know what a carboxylic acid looks like, right? We've kind of got that down by now. All right, replacement of this OH group, this alcohol group with different groups, all right, we can do this, and it usually is not going to involve a change in the oxidation state. If the new group we're going to replace it with, let's call it Z, is a heteroatom. All right, compounds of this type where the oxidation state is not changed are called carboxylic acid derivatives. All right, the 5 common types of carboxylic acid derivatives are acid halides, acid anhydrides, esters, amides, and nitriles. All right, and we're going to cover each one of these in great detail in regards to their preparation, their properties, and their reaction. But first, we're going to start off with nomenclature, making sure we know how to name acid halides, acid anhydrides, esters, amides, and nitriles. So that's what we're going to cover on this page here pretty quickly before we jump into reactions and preparation methods of these carboxylic derivatives. Now, for naming acid halides, all right, acid halides are named as derivatives of carboxylic acids by replacing the suffix -ix acid, all right, by replacing this part with -il and the name of the halide. So this is a carboxylic acid. If we convert it to an acid halide, all right, it will no longer be called acetic acid. Instead, it'll be called acetyl and the name of the halide you have. We have bromine here, so this will be acetyl bromide. Now, when the acid halide group is attached to a ring, the suffix carboxylic acid, all right, this -ic acid will be replaced with carbonyl halide. So here's what this carboxylic ring structure is called: benzoic acid. If we replace it with a chlorine, it's going to be named benzoyl with this YL instead of IC and the name of the halide. Here it's chlorine, so it'll be chloride. All right. Now, for naming acid anhydrides, all right, for naming acid anhydrides, they are named as derivatives of carboxylic acids by replacing the acid simply with anhydride. All right, that's pretty easy. So if you're replacing this OH group, all right, and you're forming an acid anhydride, instead of saying acetic acid, you're going to say acetic anhydride. Same rule applies for longer ring structures as well, and ring structures. All right, now for esters. All right, for esters, esters are named by first indicating that the alkyl group attached to the oxygen followed by the carboxylic acid. So for which the suffix is IC, we're going to replace it with 8. All right, so this is acetic acid. All right, we're going to replace this OH. We're going to keep the oxygen, but we're going to add some alkyl group here. So we're going to change the naming of this to first state what the alkyl group we are attaching is called. Here, this is a 2-carbon alkyl group. So this is going to be ethyl. And then we're going to change the name completely to acetate to indicate this new formed ester derivative. All right. Now, for ring structures, here we have benzoic acid. All right. Oh, I'm sorry. I'm jumping to amides. Now, for amides, naming amides as derivatives of carboxylic acids, all right, you're going to replace the IC acid part of the name to amide. All right, so here we have acetic acid. Okay, we're replacing this OH with an amide group, so we have to change the name from ic acid to amide. So from acetic acid to acetamide. Now, when the amide group is connected to a ring, the suffix is replaced also with amide. So here we have benzoic acid, right? This is a ring structure with a carboxylic acid attached to it. We're going to change this OH group to an amide group. So we're going to change the name from benzoic acid to benzamide. All right, that is how naming will be done for amide carboxylic acid derivatives. Okay, now for naming nitriles, nitriles are named as derivatives of carboxylic acids by replacing the ic acid either with oic acid or O-nitrile. All right, O-nitrile is the most common one used. So here's our acetic acid. We're going to replace this OH group with a CN group. All right, now in doing so, we're going to change the name from acetic acid to acetonitrile. All right, same goes for ring structure. Here's our benzoic acid. We're going to convert this to nitrile completely. All right, it's going to go from being called benzoic acid to benzonitrile. All right, and these are some of the nomenclature rules for carboxylic acids. All right, do some problems just to get yourself kind of familiar with how the rules will go into play with all your different carboxylic acid groups. All right, now what we want to talk about, is similar to the previous chapters where we talked about nucleophilic reactions of, say, in our previous chapter, ketones and aldehydes. We want to have that same discussion with carboxylic acids and their derivatives. All right, we want to have the same discussion. Now, the reactivity of carboxylic acid derivatives is pretty similar to the reactivity of aldehydes and ketones in a number of ways. In both classes, that carbonyl group that we have is electrophilic. The carbon of the carbonyl group is electrophilic, and it's going to be subject to attack by a nucleophile. In both cases, the same rules and principles kind of govern the proton transfers that accompany the reactions, and we're going to see that soon. But there is one critical difference between carboxylic acid derivatives and ketones and aldehydes. Specifically, carboxylic acid derivatives possess a heteroatom. All right, they're going to possess a heteroatom, whether it be a halide or an amide group. All right, the carboxylic acid derivatives are going to possess a heteroatom that can function as a leaving group, whereas when we talked about aldehydes and ketones, they did not possess this. Now, so when a nucleophile attacks a carboxylic acid derivative, that nucleophile can actually replace the leaving group, and this reaction is called nucleophilic acyl substitution. In summary, nucleophilic acyl substitution reactions occur via a mechanism that's going to involve 2 key steps. Nucleophilic attack, where your nucleophile is going to attack the electrophilic carbon here. All right, and that double bond is going to dump its electrons on the oxygen. Now what you have is this tetrahedral intermediate. And we notice something important here. All right, when a nucleophile has attacked that carbonyl group to form a tetrahedral intermediate, the carbonyl group will be reformed. And this is reformed in our second step. All right, it'll be reformed because the oxygen, that lone pair in the oxygen is going to reform that double bond, and we're going to have loss of a leaving group. All right, if possible, hydrogens and carbon groups are generally not going to be expelled as leaving groups. Other things are going to be expelled as leaving groups. This is usually in your carboxylic acid groups going to be that chlorine or that anhydride, so on and so forth. All right, and then you're going to form your product. All right, so you have nucleophilic attack, loss of a leaving group. Now, sometimes when you're drawing out the full mechanism of this, there might be intermediate steps of proton transfers to make sure that if you're conducting this reaction in an acid environment, you're not forming bases. And if you're doing these mechanisms in basic compounds, you're not forming acids. All right, so just letting you know. Now, a few more notes really quickly before we jump into some practice problems here. All right, I'm just going to restate some of the things we have already covered. All right. And I want to move into this page right here really quickly before we do practice problems. All right, a few more notes on nucleophilic acyl substitution. The general reactions for these conversions are as follows. You can replace leaving groups and stick new groups for carboxylic acids or their derivatives. So you can react with nucleophiles that will replace whatever heteroatom you have here in your carboxylic acid derivative into a new group here. All right, you can replace it and you can reform carboxylic acid, or you can form other carboxylic acid derivatives with a starting material that is a carboxylic acid derivative. All right, now most reactive acyl compounds can be easily converted into the least reactive ones. Okay, for example, our acid halides, are the most reactive carboxylic acid derivatives. They can be converted into other groups that are less reactive. So we can convert our acid halide into an anhydride or an ester or our carboxylic acid or our amide and so on and so forth. Okay, so your most reactive can be converted to anything that is less reactive than it. All right, for our anhydride, all right, let's highlight that in red. You can convert anhydride into any other carboxylic acid derivative that is less reactive than it. And just to make this easier, carboxylic acid conversions is going to allow for the switching of back and forth. Okay, now we're going to scroll back up. Okay, really quickly. Here is the hierarchy for most reactive to least reactive. Your acid halides are most reactive, followed by anhydride next up, then your esters, then your amides, and your nitriles are least reactive. So reactivity increases from the bottom up here on how I have them listed. All right, now let's do some practice problems here. Okay, this question is going to ask us something specific. It's going to say propose a plausible mechanism for this transformation. All right, so not only do we have to figure out how to get from starting material to end, but we have to draw the mechanism for this. Fantastic, we know how to do this, okay? We're going to follow sort of the baseline here of nucleophilic attack and loss of a leaving group, and we're going to kind of draw that out for this problem here, okay? Here is our starting material. We're going to go ahead and we're going to draw it. It's an acid halide, specifically a halide, specifically an acid chloride. We're going to react it with this nucleophile here. All right, we're going to treat it with this nucleophile here. Now, first step is, of course, this nucleophile is going to attack the electrophilic carbon here of the carbonyl group. And this double bond is going to break and dump its electrons on the oxygen. What that means is we form this tetrahedral intermediate we've seen before. All right, where we still have our chlorine group attached, and this oxygen has 3 lone pairs of negative charge. All right, what's going to happen here is now we're going to take this lone pair, we're going to reform the double bond. And what's going to leave is the best leaving group, which is this halide group right here. All right, so our chlorine group is going to leave, and what we end up with is the product that we wanted to form. All right, fantastic, this anhydride structure. All right, notice the reason why, if you start with acid halide, which is your most reactive carboxylic acid derivative, you can convert it to any one of these, because if you attack it with the group that is going to form your anhydride, like you see in this synthesis problem, your chlorine is your best leaving group and will leave, so you can form this anhydride. All right, it's why it's harder to start with an anhydride and try to form an acid halide. Because when you try to attack an anhydride with a chlorine group, in the process where you're reforming the carbonyl group, your chlorine will leave again and you'll just be reforming anhydride. This is why it's important to understand the trend of reactivity here, most reactive to least reactive. All right, your most reactive carboxylic acid derivatives, you can take it and convert it to any other. But as you go down your reactivity, it's harder to form more of these carboxylic acid derivatives. All right, for now, we're going to end here. In our next session, we're going to go and focus on every carboxylic derivative from acid halide to anhydride, ester, amide, and nitrile. We're going to build a profile for each one of these. All right, and we're going to learn reactions that we can do for each and do practice problems for each. So we're going to build a profile for acid halides, esters, anhydrides, amides, and nitriles in the realm of carboxylic acid derivatives. Let me know if you have any questions on this session. Happy studying and good luck.